First, let me introduce our speaker. So today, we are pleased to invite Professor Witold Nazarewicz to Fudan Open Seminar. So Dr. Witold Nazarewicz is a John Hanna Distinguished Professor at the Michigan State University and the Chief Scientist of FRIC. So from 1999 to 2012, he served as the Scientific Director of the Oak Ridge National Lab, Holyfield Radioactive Ion Beam Facilities. Until 2014, he was James McConnell Distinguished Professor in Physics at the University of Tennessee, Knoxville, and the Professor of Physics, Warsaw University, Poland. He has held several visiting positions, including professorship at Lund University, the University of Cologne, Kyoto University, the University of Liverpool, and the Peking University. Dr. Nazarewicz has received countless honors, including the Fellow of American Physics Society, the UK Institute of Physics, the American Association for the Advancement of Science, etc. Dr. Nazarewicz specializes in many fields, including nuclear structure, quantum manipulation problem, and the physics of open systems. As the FRIC chief scientist, he advised the project directors on issues related to the important science and ensure that the FRIC research program remains at the cutting edge of the field. So far, Dr. Nazarewicz is the author of 9 review papers and more than 420 refereed publications in scientific journals, with more than 28,000 citations and the H-index of 89 according to the Web of Science. Today, he will introduce artificial intelligence and machine learning in nuclear structure theory. So I think now is your turn, Witold, please.
Simeon, thank you very much for this very kind introduction, and I'm so happy to be able to give this talk at Fudan University on artificial intelligence. So unfortunately, COVID is not gone yet, so we cannot travel freely wherever we want, but hopefully in a not too distant future, it will be possible to visit China again. I will be very happy to see my friends in China. So today I'm going to talk about machine learning. The title has artificial intelligence too. There's not a lot of artificial intelligence in nuclear structures, nuclear theory yet, but machine learning is a part of artificial intelligence. It's a sub area of AI. So could those colleagues who have microphones on, could you unmute, please? Because I can hear voices. So I'm going to start from some general ideas, definitions, and discuss why do we do it and how is it done. I will present examples of recent work, and I will end with some perspectives. So if someone will have burning questions, please do not hesitate and ask during my talk. And of course, there will be some time for discussion after the presentation. So let us start. So this diagram shows the place of machine learning in the big picture scale of nuclear science. So on the left-hand side, you have the areas of nuclear physics, such as fundamental hot and dense nuclear matter, physics of hadrons, medium energy physics, physics of the atomic nucleus, and nuclei in the cosmos, and physics of fundamental interactions. Well, machine learning is the area of science which deals with automated processes that learn by example in order to classify, predict, discover, and generate new data. So we are talking about computer software that can learn autonomously. So we are talking about the connection between domain science, such as nuclear physics, and sciences such as computer science, numerical methods, and statistical science, and data science. So this is really fairly interdisciplinary area. So this diagram shows the cycle of the scientific method. Scientific method is basically a continuous interaction between nuclear experiment and nuclear theory. Nuclear experiment creates new data which challenge nuclear theory. Nuclear theory tries to interpret this data, describe the data, and make predictions, and then feeds into experiment. Experiment then tests those predictions, and this continues until theory becomes really very good and no new data are needed. Well, this is not going to happen anytime soon in nuclear science, because nuclear theory is still fairly phenomenological and continuously needs new experimental data. Here I place artificial intelligence and machine learning is somewhere in between, because it is used both in nuclear theory. Artificial intelligence and machine learning is used in nuclear experiments, for instance, in detector response and in accelerator science, okay? So it's present on many levels of nuclear physics. And there is a special box which is called experimental design. This is as close as we can get to artificial intelligence. That is, to combine nuclear theory with nuclear experimentation in a dynamic way, that theory can basically help experiment, online. So nuclear models can provide feedback to experiment while experiment is being planned and carried out, okay? And as a result of experiments and theory, nuclear data are generated. Experimental data, theoretical data. Sometimes machine learning is used for data mining, that is producing new data, which are missing, which cannot be easily measured. Okay, and of course, visualization is also a big part of the game. So, as an output here, we have discoveries, and we have societal applications. That is, applications of nuclear science to society. So, as illustrated by this diagram, machine learning helps speeding up the cycle of the scientific method. Okay, so because of machine learning, we can go between nuclear experiment and nuclear theory much faster, and we can get answers much faster, and we can optimize our discoveries. Okay, beam time and computer cycles are expensive, so in this way we can speed it up. So this figure which I showed is going to be published in RefMod Physics colloquium on machine learning in nuclear physics. So this colloquium is also posted on the archive, so it should appear very soon. I think it will appear at the end of this month or in the beginning of September. So I invite you to go to this paper and to check the volume of references on various areas of applications of machine learning in nuclear physics, in diverse areas of nuclear physics. Okay, so this is talk on applications of machine learning to nuclear theory. So I should perhaps start from nuclear theory. And this diagram shows, this is a compulsory diagram for a nuclear theory talk. It shows degrees of freedom of nuclear science, which starts from quarks and gluons, then constituent quarks, which in this picture we eliminate or integrate out gluons. And then as we go down the energy scale, we can talk about protons and neutrons exchanging pions to interact. So this is picture of baryons and mesons. And then going down in energy, we are approaching nuclear structure. That is the nucleus, which is a cluster of protons and neutrons, or contains proton and neutron liquids, nucleonic densities and currents, okay? And as we go to extremely small energies, like low-lying collective states of the nucleus, we can talk about collective excitations, rotational, vibrational states. And each of those scales, energy scales, we have different models, like lattice QCD appears here, phenomenological quark models here, various many-body approaches, okay, configuration interaction or our shell model, density functional theory, and collective models, okay. So the resolution of the model goes in this way, together with energy, okay. Simplicity goes in this way. And this equation tells you roughly the scale of the problem, okay. So for the nucleus, which has A particles, N neutrons and Z protons, the nuclear problem corresponds to so many coupled integral differential equations in 3A dimensions. So you can see that this problem becomes quickly intractable if you would like to solve it exactly. Okay, so just plug in, for the students, plug in 208, 82, and 26 here and calculate this number. So clearly, Hilbert space truncations are necessary. We have to simplify the problem by making truncations, okay? Which is what nuclear theory does, right? On the right-hand side, shown is also a nuclear many-body problem in a schematic way. So again, so this is the resolution scale, which goes in opposite direction from here. Okay, so very low resolution. So this is a very, very simple model of the reality, and the reality is here, which is marked by experiment, because experiment deals with reality. So this is a very simple picture of the reality. Okay, it is not a bad model here, you know, if you're, because the model always depends on your questions. If you are interested on whether this cow, you know, is black and white, this model will give you this answer. If you are interested in the answer whether the cow is spherical or not, this model is absolutely perfect for this. But admittedly, it's very simple, okay? And we can of course make model more and more complicated. So this is a more realistic version of this model. This simple model can be used as emulator, that is, to provide quick guesses, which can simplify our life. And this is a far more complex model, which contains more or less all physical elements of the reality. Okay. So the message from this slide is that nuclear theory needs truncations, needs simplifications, models have to be developed, emulators, that is simplified versions of the model, have to be developed if we want to make contact with reality or experiment. Okay, so why do we need machine learning in low energy nuclear theory. Okay, so we need to develop tools which can speed up our calculations and this contact with experiment. Those machine learning enables fast emulations for big simulations. It reveals the information content of measured observables with respect to theory. So experiment provides data, and what is the impact of this data on theory? Okay, so machine learning can quantify this question. Through machine learning, we can identify crucial experimental data for better constraining theory and provide meaningful input to applications and planned measurements. Of course, machine learning can also help us to reveal the true structure of our models through parameter estimation with heterogeneous data sets, model reduction, and machine learning also can help us to provide predictive capability. So it can help dealing with extrapolations and truncations. Machine learning can us provide uncertainty quantification. That is, to provide error bars on our predictions. Because honestly, if your model produces just a prediction without error bars, we are still in the dark. Okay? And then theoretical models are often applied to entirely new nuclear systems through massive extrapolations, which, the conditions which are not accessible by experiments, like supernova modeling, such as modeling of the reactor's core, neutron star, or, for instance, super heavy elements. Well, I can see some questions in the chat. Well, I see questions I don't see. I can display those questions. So, Simin, if there are some burning questions, you need to tell me, okay?
I saw no questions in the chat.
Okay.
I don't know if it's a private message.
Maybe this has been already cleared, okay? So there are various techniques in machine learning for theoretical nuclear structure. The literature is already vast, okay? And this is just a short list of what people do. Various neural network applications. There are wonderful applications of Bayesian machine learning, clustering methods, ensemble methods, including random forest, etc. Dimensionality reduction, reduction of the model parameters, and classification and regression analysis. Each of those approaches is an area in itself. So I have no time to define those. So here I refer to the review, which I mentioned, okay? So what are the typical application of machine learning in nuclear structure theory? For instance, machine learning for data mining. So theories carry out accurate calculations of observables that have not been measured to supplement the existing experimental database. There are applications of nuclear density functional theory, especially density functional calibrations and emulation of DFT results for large-scale surveys, various calculations of nuclear properties with machine learning, then effective field theory for applications in effective field theory and A-body systems. Let me disconnect the phone. Okay, applications in nuclear shell model to quantify the matrix elements, applications of machine learning to nuclear reactions, various studies. Oh, sorry. Various studies of equation of state and neutron star physics, And finally, experimental design. I will comment on experimental design later. Okay, so one of the first papers, nuclear theory papers on machine learning. So this is the paper from 1992 by Gazula and Clark and Bohr from St. Louis and from Urbana. And this is the early application of neural networks. So they started in 1991, paper appeared in 1992, and they use back propagation learning algorithm, okay, in the form of neural networks to study nuclear masses, okay? And they said that by using neural networks, one can make extrapolations or interpolations, model-based interpolation with very high accuracy, okay? So this started very early, but it's really, so the machine learning really started being noticeable in nuclear structure during last 5 years or so, when we have seen the explosion of papers on machine learning in various nuclear structure applications. So now I would like to show you selected examples, okay? So this is the example. There are two examples which pertain to extrapolations of A-body results using artificial neural networks. So here is recent paper by Yoshida, and here he's using basically the ab initio approach with 2- and 3-body interactions, 2- and 3-body nuclear force, both chiral force and more conventional force. And here you see the results for lithium-6 at the various level of truncation. And then max is the oscillator basis truncation here, okay? And you can see that for various forces, machine learning provides a speedy answer together with uncertainties. So we can see energy together with error bar here. And the error bar, of course, depends on the interaction used. So with machine learning, Yoshida could go to 18 oscillator cells here. You have another example, similar problem, okay? These are calculations for helium-4 with no core shell model, again with chiral force, the same for oxygen-16. And here shown is basically uncertainty of calculated energy. Okay, here is the energy of oxygen-16, again as a function of basis truncation. So machine learning has been used in sensitivity studies and in the model calibration. So how to optimize model parameters and how to understand structure of a model. Okay, so this diagram, which was actually obtained in 2014, showed the result of the model calibration of energy density functional. So for the calibration, various kinds of data were used on masses, radii, pairing gaps, fission isomers, and single particle energies. And here are the model parameters. And the bar tells you which data is most crucial for those parameters. For instance, as you can see, for proton and neutron pairing, for instance, very important are odd-even mass differences, as one would expect. But for various quantities, different experimental quantities impact the parameters rather democratically. This kind of analysis can give you some guidance of what is needed for your model to make to be better constrained. So this is, oh, my mouse, sorry. sorry, my mouse got out of control. I have to. Okay, so I will try to minimize mouse motions. So this paper by Fox shows results of shell model calculations in which matrix elements were actually quantified, okay, with error bars, and this shows the error bars on binding energies of various nuclei obtained in the shell model. And the lowest diagram, this diagram shows the predictions of energies and radii of a light nucleus, okay, now depending on various parameters of the chiral force. And for instance, as you can see, this parameter here, this is for this S1, this is triplet, spin triplet parameter, primarily impacts the energy of the system, because the details are in this paper. So this is an example of Monte Carlo calculations for lithium-6. Though this is a six-body problem, here neural networks were used in the variational way. So these are quantum Monte Carlo calculations using variational Monte Carlo, VMC, okay? So this is variational Monte Carlo. And the wave function was parameterized using many parameters, and the problem was minimized using artificial neural networks, okay? The first calculations, first approach, first applications of this approach was for deuteron by Sari group, and this is a more advanced example for mass 6 system lithium-6. And as you can see, exact or more exact calculations using hyperspherical hyperharmonics HH. This is only with two-body force, and this is with three-body force. Okay, this variational approach using machine learning gives you really very good description of the system. And this is an example of large-scale density functional theory calculations with artificial neural network. So the point of this paper here is, if you are interested in a global survey, it is perhaps not necessary, not needed to do calculations for every nucleus in a data set. Here, in the first step, we identify the nuclei which will be used for training. So this is the upper panel, okay? So training set is the 10% of the data set, okay? So for those nuclei, we carry out DFT calculations, and in the next step, we basically use neural networks to interpolate between those nuclei from the training data set. So we are training DFT emulator using 10% of nuclei, and we make predictions for the remaining ones. And you can see that those predictions are really very good. So this is root mean square error on the total energy. And we see that for most of the system, actually this kind of approach, which admittedly speeds up everything dramatically, works very well. This is the example actually of predictions for nuclear data. Those are actually two nice examples of work done by Chinese groups, okay? The left diagram shows the predictions of fission yields, okay? So those are the fission fragment yields as a function of mass number for a number of systems, uranium, plutonium, thorium, okay? And the model, this is compared to phenomenological model called Yandel, okay? And you can see that machine learning does extremely well. So you can use this tool to make predictions for yields, for instance, for nuclei which have not been measured. On the right-hand diagram, shown are predictions of nuclear beta decays, half-lives, with Bayesian neural networks, okay? And using this approach, you can make extrapolations to unknown nuclei, for instance, on the path of the R process. And this diagram also nicely shows that predictions are carried out with error bars, okay? So those are the predictions with error bars, so uncertainty is also provided. Right, I would like to make a comment that many machine learning approaches basically does extrapolation and interpolation fairly blindly. You know, many people use machine learning as a black box, like in this joke here. And the guy is mining data, as you can see. So this is your machine learning system. Yep. You put the data into this big pile of linear algebra, then collect the answers on the other side. Here it comes, here it goes. What if the answers are wrong? Just sit, stir the pile until they start looking right. So it's very important for us to understand what is happening. The question of interpretability, right? And interpretability, especially in physics, is the key. So here I would like to advocate for Bayesian approaches, because Bayesian inference dramatically increases interpretability and accuracy. So for each of those machine learning approaches, which are shown here, okay, there exists a Bayesian counterpart, which can be used. We can use neural networks, we can use Bayesian neural networks, and by doing this, we can learn on how to interpret the machine learning tool. Okay, so well, I have really no time to give a primer on Bayesian inference. I just wanted to show this famous Bayes equation. Okay, so what we would like to learn, about quantity A based on assumptions that B, some facts B are true, okay? So this incorporates, this probability incorporates our current knowledge on this quantity A, our belief in how B looks given A, and model evidence, okay? So this is, I cannot, of course, talk too much about it because this would be a very long talk, but there are this is used, Bayesian approach is used when we are dealing with models with many parameters. We need to understand the meaning of those parameters. We need to understand the range of those parameters. So models are described by means of coupling constant theta. So any predicted quantity by a model, of course, is a function of those parameters. And since the models were optimized using the finite set of data, of course, there are correlation and uncertainties. And so sometimes the task is to understand those parameters, their ranges, and corresponding errors on predictions, right? So here you have an example of such a work. This is a 12-dimensional space of density, or nuclear density functional. This one is called UniDef1, and those are various parameters, and those bivariate marginal estimates show this spread in those parameters, okay, around the optimal value. Optimal value, of course, gives you given parameterization, but there are uncertainties around this optimal value. But now you can see how those parameters are distributed and how are they correlated. Some of those parameters are like those two here are extremely well correlated. Then you can take those posterior distributions, as we call them, and then carry out calculations for quantities of interest. Here, for instance, this very data or input was used to calculate our process abundances. So what one can do you can use this as an input and randomly select models based on those distributions, carry out our process simulations, and as on the output, you will get predictions together with uncertainties, okay? Right. You can also use a Bayesian approach to fix model imperfections, okay? So this is a prediction of your favorite model, and this is experiment, this is experimental data. So the difference between your model prediction and experiment is called residual, is discrepancy, okay? This is this D, and it has two sources of error. One is experimental error, and one is theory uncertainty. In many applications of nuclear theory, theory uncertainty is definitely dominant part, especially systematic part. So one good strategy is to take this difference and then develop a model for this difference, develop the model for the residual. This is often statistical approach involving Gaussian processes, for instance, and then using the model for D, you can make extrapolations and predictions. So this is an example of such a strategy. So let us, this paper talks about nuclear masses. Here you have those differences between experimental and theoretical masses for various models. You can see that some of those models are extremely well calibrated, like this, very small difference between experiment and theory, some not, okay? But now we are taking these differences, those residuals, we use statistical approach, we model this difference, and we can make extrapolations, okay? In this particular calculations, testing set are the nuclei marked dark blue or red. Training set is all those nuclei for which masses are known, and now we can make extrapolations. There are some technical details about the Gaussian processes used, okay? We used some features to inform the model for residuals, okay? But here you have the outcome, you have predicted masses, extrapolated masses, right? And with error bars, with uncertainties. And if you do it right, it does not matter whether your model was extremely well calibrated, whether it was fitted to the data like crazy, or whether it was contained finite number of parameters. The predictions, as you can see, are fairly close. Okay, so I have some discussion here about Bayesian model mixing, because usually the way we analyze the data, we make predictions with various models, and models, we plot those predictions, and then we believe that we see some trends. This is, of course, statistically a very poor approach. A better way is to combine models in scientific way. And this is the area of Bayesian model averaging, okay? So Bayesian model averaging is used in many fields, including weather forecasting, political science, transportation, and of course, nuclear structure. And here are examples of papers which use this Bayesian model mixing and averaging. So in essence, what one has to do, one has to calibrate models. We have M with the superscript K, stands for a model number K. So for each model, one can establish parameters to do model calibrations, and the final result will be basically a superposition of individual model results. Okay, so this is called Bayesian model averaging. Is a more advanced way of doing things is called Bayesian model mixing, in which we assume that the true model is a combination of all those imperfect models here. Okay, so an early example of this model averaging was basically a prediction of the calcium chain. So calcium-60 was discovered at Riken, and the question which was asked in this paper was, what can we conclude from the fact that calcium-60 was observed? Okay, so in this paper we used this approach of Bayesian model averaging, and this is the final result. It shows the probability that a given nucleus exists, that is neutron bound. So if the color is dark green, it means that all those models which are used, like 11 models in this case, you know, they predict a nucleus to be neutron bound with 100%. So the drip line would correspond to 50% probability. Okay, so that the statistical analysis tells us that, for instance, calcium-70 is bound by more than 50%. Okay, so based on such calculations, which correspond really to enormous extrapolations, we can provide some guidance to future experiments. Go for calcium-70. Perhaps it exists. Okay, and this is the whole nuclear landscape, the whole chart of the nuclides. Okay, you see this probability of existence for every nucleus in the nuclear chart up to Z119. Okay, and this spread here also indicates the current theoretical uncertainty on the drip lines. Very nice Bayesian analysis of the nuclear matter equation of state and structure of neutron stars. Here in this particular paper from 2020, okay, various kinds of data were used, like data on very heavy neutron stars. The LIGO data, okay, from this gravitational wave detection, the radii data from NICER, okay, and all this data together with nuclear physics observations, okay, can be combined to produce uncertainty bands on masses and radii of neutron stars on the equation of state, which is pressure versus energy density. Okay, so I'm approaching the end. Okay, I just would like to emphasize that uncertainties are absolutely crucial. Okay, so this diagram makes this point very nicely. Those are the matrix elements for neutrinoless double beta decay calculated using different models, okay, of various kinds: ab initio models, DFT models, algebraic models, etc. And you see that those matrix elements are really all over the place, right? With various, you know, for various nuclei, you have tremendous ranges of those matrix elements. And this matrix element M0 nu appears, you know, in some power when estimating the amount of material needed for your germanium or xenon detector, right? So it does matter whether you need 1 ton of the material or 10 tons, right? And right now, those predictions are just numbers, okay? Or if there are errors, those are the errors due to, say, cutoff or truncation scheme. But what I would like to say that perhaps if you will honestly compute answers of all those models, it will turn out that all those models are totally consistent with each other, that they are within similar error bars, and they are not extremely useful for experiment, okay? So we need to work harder in order to provide predictions with well-defined uncertainties, okay? And the best, of course, would be to mix all those models to provide one answer with hopefully small error bar. And this is what the band collaboration is. I really invite you to go to this website, band framework, So this is the collaboration involving several nuclear theory groups and also statisticians, okay? And the goal of this collaboration is to develop Bayesian software for structure and dynamics of atomic nuclei. And this is actually the diagram which shows the plan, big scheme of things, which you can read in this Band manifesto, which was published last year. And the last thing I wanted to mention is something, in my opinion, which is something which is the future of the field, is this experimental design, which will help both experiment and theory, okay? So imagine you would like to measure some quantity, but you are not sure in how many points, what are the kinematic conditions, what are the angles, what are the energies, okay? And how can you optimize your run, okay? But there exists a model, or exist several models, which can perhaps provide the guidance. So the trick is to provide the utility function, which is designed to encode the goals of the experiment and the constraints which are inherent in carrying it out. For instance, we have only certain detectors available, okay, and we got only 10 weeks, 10 days of beam time. How can we optimize things using our current knowledge and the experimental realities, okay? Once you identify this utility function, okay, which corresponds to various designs of the experiment, you can try to optimize it or minimize it, okay? Then it becomes machine learning process, okay? And this is an example of such work. This is the application of machine learning to proton-compton scattering. And according to theory, in order to maximize experiment, you need to do calculations in those points marked by dots here, okay? You will get the maximum out of your run. Okay, so it's time to finish. There is a huge need for machine learning and uncertainty quantification in nuclear physics theory. Okay, there exist various approaches which are used in numerous applications in almost every area of nuclear science. Machine learning has been successfully applied. Okay, it's very good gradient. If you will read this remote physics colloquium, you would see the huge amount of literature already existing on this topic. Okay, but we need to speed up the cycle of the scientific process. You know, if we want to produce exciting physics in finite time, okay, so machine learning is badly needed. We need the teams which will involve not only nuclear theorists and experimentalists, but also statisticians, computational scientists, and applied mathematicians. This is very important. And we also need to educate the community. We need to talk about those tools, you know, and that's basically what I wanted to say. Thank you very much for your kind patience.
Thank you very much for the very nice talk. So now I think it's question time. So if someone has questions, please raise your hand or unmute yourself. Okay, Marienzo, please.
Hi, Witold. So very nice talk. So I'm very interested about your Bayesian modeling, mixing or averaging. So about that, this part, I remember, if I remember correctly, there's around 11 or more models they will mix together, right?
Yes. So you have several models, and you can make predictions for all those models. Okay.
So also these models, they are they are the same. Are they the same physical model but with different parameter, or they are
okay. So this is
different models?
This is very good question, right? Because you can argue that when you have one skerm functional, so this is one model, and this skerm functional was optimized using certain data set. So I completely agree. So what you would like to do, you would like to take very large data set, the largest possible, which you believe is important for your physics. And then you would like to calibrate the functional, the square functional. You can obtain those posterior distributions of parameters, okay? And you can call it just a square model. You do not have to attach to it, any name, because this will represent all square functionals which exist. And you do the same with relativistic mean field, right? Approach. And you can do it with non-standard functional, such as, for instance, Fayence functional, which is based on slightly different principles. And then you can do the same with one of your ab initio models, like coupled cluster model. Then you have several models which are based on different assumptions, okay? You can use each of those models to calculate the same kind of data. And then when you mix those models, you believe that those models are fairly orthogonal, okay? So what we are doing right now is not this. We just take current models, we basically move around the minima of those models, okay? But this is not the way BMA should be used, okay? So these are the first works on this topic.
Okay, okay.
So let me finish it. You need to orthogonalize, you really need to orthogonalize those models. And there is a way of doing this using principal component analysis. You basically take different models, you make predictions for those models, and then you do principal value decomposition. And this will tell you to what extent those models are similar or not. Okay?
Yeah. Okay, okay. And thank you for this question. And there's another general question that I'm curious for many years. That what do you think about the relationship between fitting and machine learning? Since most of they can do the extrapolations uncertainty analysis.
Between machine learning and what? And fitting.
And fitting.
No. Okay. So fitting is usually based on some standard statistical approach, like a linear regression, right? So so fitting or linear regression, okay, is like a very poor man's machine learning. What you do, you got your minimum, but you can, of course, based on the shape of your chi-square as a function of the parameters, you can establish covariances. And from the covariances, you can get ideas about errors, okay? So imagine that your model is extremely well calibrated, and then that in every direction, your posterior, okay, looks like a Gaussian.
Okay.
So this is, so if your model is extremely well calibrated, if you are Gaussian in every direction, then Bayesian approach will be very similar. Okay, Bayesian machine learning will be similar to your calibration approach.
Okay.
But of course, Bayesian approach is general, and when you do calibration, you really assume that everything is Gaussian, which is not the case, as you could see in my example. Some of those parameters are very well picked. Some of those parameters are not very well.
Yes.
Okay.
Okay. Thank you very much.
Okay.
I think next question is from Pei Laoshi, please.
Yes, very good talk, Witold. Maybe firstly I have some.
Thank you, Pei. It's good to see you.
So, for example, as I know from compared to other physics subfield, for example, I think physical real C, we have much fewer work on machine learning compared to physical real A and physical real B and other fields. So I think one problem is that in nuclear physics we have very few data, and we are very difficult to get the nuclear data. Nuclear data is very expensive to obtain by experiments. So I think this is one problem to that is difficult for nuclear physics to apply machine learning.
Well, I think I think this is opportunity, right, for theory. As you know, the data are expensive, can be taken in only a few points. So why don't we take our best models, calibrate them properly, okay, that they describe the current data, and use them to provide the missing data, as you know very well, because this is what we are doing for fission.
Yes. So another question that you have mentioned, the Bayes machine learning. I think in most of the cases, Bayes machine learning, people are optimize the likelihood function, and it's difficult. We should do to optimize the positive function, but it's difficult to do that.
Well, you know, physics should not really depend on your prior, right? But in practice, it does, okay? Because if you have unrealistic prior, this will give you unrealistic posterior. So if you do properly statistical, you know, Bayesian approach, you have a number of hyperparameters which describe your prior, right? And you should really integrate of all those parameters when making predictions. So yes, how do you get your prior? It depends on your experience. Okay. It depends on your model used. There's no general recipe for the prior. But I completely agree, Pei, with you that the choice of prior is crucial. Okay.
Yes. Thank you. Yeah.
Okay.
Next, I think is 刘老师，您请。
Okay, Witold, can you hear me?
Yes, I can hear you very well.
Yeah, this is Wei Liu from CIE. So I'm an experimentalist, and I have one question and one comment. My first question is that you said that once machine learning is began, it fell into so-called black box. But in the future improvement, could it be possible that people can guide the development inside black box by some simple conservation law, like energy conservation, angular momentum conservation, not complex quantum mechanics? Then somehow that could be improve the correctness of those black box. This is my question. The comment is that in the end of your talk, you showed that the metric element of different theory for neutrinoless double beta decay is quite scattered. I just naively thinking that since nuclear physics and quantum physics are the same for those isotopes, could that be educated guess to draw a kind of line, a very smooth line in the center of those scattered metric elements? Thank you.
Well, let me start from your first question, and then I will address the neutrinoless physics next. So your first question is, we need to put as much physics or intuition information into the black box. Actually, I don't like
absolutely.
Boxes. I personally, I'm not great fan of just naive neural network calculations or black box calculations, you know, which just provide you with some numbers. I really like Bayesian approach, which can provide you uncertainties. Okay, and there's a lot of way. But if you really insist in doing your black box, yes, symmetries are important, conservation roles are important,
yes.
And there are also various features, right? Features which you can use to educate your black box.
Yeah.
For instance, you know that that shell structure in nuclei exists. You know that odd mass nuclei have higher binding energies than even mass nuclei. You can implement these general features, okay, into your black box. So it will become a little bit less black, okay?
Yeah, yes.
So I think the feature machine learning is important. Then your second question, okay, there's a lot of discussion right now about the diagram which I showed about neutrinoless double beta decay. We just finished a report which you can find on the archive, okay? It involves a bunch of people interested in Bayesian statistics, nuclear structure physicists, and also people who do effective field theory, lattice, and nuclear structure calculations, okay? So I think that so by Cyriliano and Phillips and Engel and myself, you can find it on the archive. It has just been posted. We intend to send it to the Journal of Physics G, and it explains it explains the strategy. What do we need to do in order to get this consistent answer for matrix element?
Yeah. Yes.
So here I can just refer you to this paper. It's not extremely long, but it contains two diagrams which show the strategy. Okay.
Okay. Thank you so much.
No problem.
Okay. Next one is Ma Long Laos, please.
Hi, Witold. Yeah, thank you for your excellent talk. So on your presentation slides 29, so I have a question. So on the nuclear matrix element calculation.
29. Okay, so this is
29. So right. This slide. Yeah. So here, so you see here you also mentioned here the uncertainty currently the calculation uncertainty from different models is somehow huge. So do you have any suggestions so on the reducing the uncertainties from the machine learning approach? So do you have any suggestion here?
Yeah. So yes. So this is really the same answer as in the previous. So do you see my screen?
Yes.
Just do you see my talk or you see my screen?
I see the full screen.
Okay, great. So let me just give you a quick answer. Okay, I will give you a very quick answer. I will just find this paper quickly on archive. And I will show you the figure which you need to see. Okay, you see, so this is this paper towards precise and accurate calculations of neutrinoless double beta decay. So this was project scoping workshop, and now
I think you are still sharing the talk.
Oh, I'm still sharing the talk. Okay,
yes.
So let me unshare and share again. Okay.
Yeah, maybe to switch to another window, maybe.
Okay, is it okay?
Yeah. Perfect.
Now you can see the paper?
Yeah, it works.
Okay, it works, very good. So now you can see, so this is this paper on the archive. It was posted in July. And this shows the general theoretical strategy. It just talks about what one still needs to learn theoretically. This shows basically the current situation when it comes to one particular beta decay. This is from calcium to titanium. So this is this system which can be calculated using various models. And I think for me, the most important plot is, hold on, you see, this is too long, a report. Yeah, is this plot, which tells you how you get from various models, okay, So you have several models. You do model development. In each case, you develop emulators using machine learning for each model, right? You calibrate the models, that is, you determine all those parameters. You get the posteriors for every model, for each model, right? And then you define the evidence data set, which will make it possible to mix those models. You get the model weights, and then based on those models, you calculate posterior distributions. And this gives you predictions with uncertainties. So this is the big picture. This is how you use various approaches, how you use machine learning, and how you use model mixing in order to get it, okay?
Okay, yeah. So yeah, maybe another question related is that because I'm working on experiment, but I know that for calculating the nuclear matrix element is kind of computing time consuming. So what about so I don't have the kind of idea how is this kind of machine learning way will reduce some time.
So important word for you is emulators. Emulator is basically a quick version of your model. So this is what I, for instance, discussed in the context of these DFT calculations when 10% of nuclei were calculated, properly, and then everything else was interpolated, right? So this is emulation of calculations. So big part of machine learning is to use machine learning tools to produce cheap versions, cheap that is not extremely computer intense, okay, versions of theoretical models. And then this problem basically disappears because once you develop good emulator, you can run it many times on your laptop. Are you satisfied with this answer?
Yeah. Oh, yeah. Okay. Thank you. I will. Yeah, I will read this paper. Yeah. Thanks.
Okay. Yeah. Very good.
So, any question else? I have a question actually. Most of the neural network or artificial intelligence, as you mentioned, are doing extrapolations or interpolations. So it's possible to use that machine learning to dig out some new physics, like analyzing those residues between theory and experiment.
Yeah. I mean, extrapolations are new physics, right?
Well,
you extrapolate to the region which has never been visited before.
Yes, that's true. But I mean, what we don't know what is the missing physics there, right?
Well. But we don't know what is missing physics. That's why we develop our models, right? Mm-hmm. When we extrapolate, we have to use our current best models, right? Mm-hmm. And then we hope that ingenious experimentalists, excited by our predictions, will go there and show that our models are not very good, okay? This is a slow process. Because, I completely agree, of course, Simin, if we are here, and if you want to go there, right, very far away, maybe situation will completely change. Think about neutron star, okay? So we believe that close to the surface, nucleonic picture works. And we have all these fantastic models of neutrons and protons at very high density and pressure, right? But as we go deeper towards the core of the neutron star, we'll have hypermatter, we'll have phase transition to completely different degrees of freedom. And as we go closer to the core, we'll have quark-gluon matter, right? So clearly, if you take nucleonic model and try to predict what happens in the core is very inappropriate, right?
Yes.
So when we make extrapolations, we must identify our assumptions very clearly. So,
I see.
and we should be very, very careful. We should be careful. And if we do things honestly, then the error bars, okay, will increase as we extrapolate more and more, okay?
I see. Yeah, thank you. So I see no more questions. So let's thank Witold again for the very nice talk, and also thank all the audience.
Okay, well, thank you very much for the opportunity to visiting you in China in this way.
Thank you.
Okay, bye-bye.
So today's seminar is over. See you next time.
Okay.